Minkowski spacetime diagrams can be very helpful for understanding relativity problems, especially for people who don't like to see a lot of math calculations. This video just has pictures. There are no calculations at all. But the diagrams do take some getting used to, so I'd like to give you a step-by-step introduction. Here's what the spacetime diagram looks like. We always put time on the vertical axis, and usually we just use one space dimension, x, and that's on the horizontal axis. The path of a light ray is always a 45-degree line. This represents, say, a little flashbulb going off at the origin, and actually what happens is the light moves out in an expanding sphere. In one dimension, that's just a line. In two dimensions, it would be a circle. And so if we put 2 dimensions on the space-time diagram, we get what looks like a cone. That's called the light cone. These are used more often in general relativity when we want to show the curvature of space-time with putting light cones in different places. But even in special relativity, when we're just using one space dimension, a lot of times we talk about the term, we use the term light cone, like the illusion has to stay within the light cone. And in that case, it just means to say between the axis and those 45-degree lines. Okay, the world line of a person or an object is the path through space-time as plotted on the Minkowski diagram. In a frame where people are not moving in space, they're just stationary, they still move through time, so the world line is a nice vertical line. This slide shows where the rest frame of both Alice and Bob, when they're different locations. Now suppose Bob flies in a rocket. In that case, his world line is tilted with respect to Alice's, because now he's moving in space as well as time. We can move Alice to where she was at the same place as Bob at time 0. We see that each person's world line is also their time axis, as long as they have no acceleration. Now to see where Bob's space axis is, remember that the speed of light is constant in both frames. So the light ray is always at half the angle between the time axis and the space axis. And as the velocity increases, what happens is that the time and space axes rotate toward each other. This is not something we can visualize, or at least I certainly can't imagine the space axis rotating toward the time axis, but we can do it mathematically. And so when we get used to the picture, it's easy to see how things work out. Now in Bob's frame, Alice is moving to the left, so her coordinates in Bob's frame are the mirror image of Bob's coordinates in her frame. Now let's look at how to change coordinates. Suppose we plot any event in space-time. It's easy to find the coordinates in the lab frame. What we do actually is we draw lines parallel to the axes and see where each one intersects the other axis. To find coordinates in a frame moving with respect to the lab frame, we do the same thing actually. We draw lines parallel to the time and space axes and see where each one intersects the other axis. This is not supposed to look normal. Just the fact that the speed of light is constant in all the reference frames is already beyond our experience. Suppose we have a space station and a rocket moving with respect to each other. They can come together, or they can be moving apart, and it can be at 99% of the speed of light. But each one, if they fire some, say, a pulsed laser toward each other, they'll both measure the same speed of light no matter what the circumstances. Now people ask, why is it that way? All I can say is, that's the universe we live in. Now notice that the distance on paper between 2 points on the Minkowski diagram doesn't mean a whole lot. The definition of a space-time interval has a minus sign in it So it's very different from ordinary Euclidean space. The space-time interval is the same in all inertial reference frames. So let's pick 2 points. It's easy to read off delta t and delta x in the lab frame just by looking at the graph. In the frame moving with respect to the lab, here's delta t, the black segment on the t prime. We generally use x prime and t prime to be the coordinates in the frame that's moving with respect to the lab. Okay, the black segment on the t prime axis is delta t prime. And then here's delta x prime. That's the black segment on the x prime axis. Now the interval in the lab frame equals the interval in the moving frame. For motion at a constant velocity with no acceleration, there is always a rest frame where the velocity is 0, so delta x equals 0. And the time there is the proper time, which is the time that your watch measures. Now let's see why both Alice and Bob see the other person's clock run slow. Bob and Alice are going to communicate by sending messages to each other at the speed of light. So to find out what time the message was sent, they have to subtract the light travel time. If this is not familiar to you, check out the video on Alice and Bob do relativity experiments. At time 0, they synchronize their clocks when they're together at the origin. Sometime later, Bob reports to Alice what time his clock reads at the event marked with a blue star. Alice corrects for the light travel time of the message Bob sent and calculates that the blue star event occurred when her clock read T2. But Bob's time was simultaneous with T1 in Alice's frame, so that's what he reported. T1 is less than T2, so Alice measures Bob's clock running slow. Now Alice reports to Bob what her clock reads at T2. This is the green star event. When Bob receives Alice's report, he corrects for light travel time and calculates the green star event was simultaneous with the event marked with a green outline star on his time axis. This is later than the blue star event in Bob's frame, so he measures Alice's clock running slow. The analysis for the relativistic length contraction is basically the same because the time and the space axes are always symmetric around the light line. So I hope this has given you a better picture of how relativity works, and thank you for watching.